Hello, everyone. Thank Claire for the introduction and thank Andy for inviting me to this mini masterclass. I'd also like to thank everybody for attending it. Today, I'm going to talk about a special case in evidence synthesis where we do not have a rich evidence base and there are only limited studies were included from systematic review for combining the results together. But the results from these studies were heterogeneous. So I will introduce you a new method which uses external information to help estimating heterogeneity in this case. As we have people from a wide background attending today's webinar, I will first give a quick introduction of evidence synthesis, the statistical methods used for combining the results, and an example to illustrate the problem we have when there's limited studies to inform decision-making. Evidence synthesis is a research tool, and it allows us to bring together all relevant information from a range of sources to answer a research question or inform decision-making. Health technology assessment is a multidisciplinary process to evaluate the clinical, economic, and broader impact of the use of health technology. Evidence on clinical effectiveness can rise from multiple sources in HTA. And for people who are familiar with HTA, you will know that most HTAs will involve some sort of a meta-analysis of studies comparing interventions of interest for the decision problem. So I will give you a quick overview on how evidence is gathered when doing evidence synthesis. The first step is to specify a research topic and develop the review protocol. Then studies are identified using a comprehensive systematic literature review. Typically, we're only interested in the randomized control studies because the results is protected by randomization, hence reduced biases. But in some cases, you may want to extend it to also include observational data or observational studies. Then studies are screened according to its inclusion and exclusion criteria, then assessed for their quality. Depending on the finding of the quality assessment, you may want to include or exclude some of the screened studies into your final analysis. Then data are extracted, ready to be used in data synthesis using some sort of meta-analysis technique. So what is a meta-analysis? A meta-analysis is actually a statistical method for combining or pooling results from multiple studies. It could be a pairwise meta-analysis where you only have two interventions of interest. In this case, we have only A and B, or network meta-analysis, NMA. In the NMA, we will have multiple treatments who are of interest, and this is often the case in HTA. The network meta-analysis allows us to incorporate both direct and indirect evidence. So for example, in this network diagram, there is a study directly comparing treatment B and treatment C. So the treatment effect of B versus C could be informed by this direct head-to-head trial. It could also be informed by the indirect evidence from the study which compared treatment A and B and another study which compared treatment A and C. Yeah, so this is the two kind of main meta-analysis we use in HTA, either pairwise meta-analysis where there are only two treatments, or network meta-analysis when there's multiple treatments are involved. So this is going to become a little bit more statistics. There are two approaches to make statistical inference. One of them is called frequentist approach, and another one is called Bayesian approach. In a frequentist approach, we only rely on data or evidence when making inferences, which is represented by this black curve. The Bayesian approach, on the other hand, uses, of course, uses the data, the evidence, the black curve, but it also allows for incorporating prior beliefs, which is represented by this red curve here. And in some cases, the prior distributions can be informed using other external evidence, not just experts' opinion. So after combining what we have seen, which is evidence in the black curve, and what we believe, which is the prior in the right curve, a posterior distribution, which is represented by this blue curve in the middle, is derived. And this posterior distribution summarizes what we learn about the quantity of interest after we've seen the data, which is in this black curve. So to summarize, a Bayesian approach is a process of updating our previous prior beliefs in red in the light of the evidence, which is in black, to obtain new or posterior beliefs on the quantities of interest. Is the final product we get is this blue curve. And one of the advantages of using a Bayesian approach instead of like the frequentist approach is that this approach is very flexible. You can fit complex models using this approach. And also this approach allows for incorporating external evidence in the form of the prior distribution. In evidence synthesis or doing meta-analysis, network meta-analysis, we normally use a called non-informative prior or vague prior for the treatment effect itself. The reason of that is we would like the data to speak itself rather than using other information to influence the estimate of the treatment effect. And when doing meta-analysis or network meta-analysis, there are two types of models we could use. One is called a fixed effect model. In the fixed effect model, it assumes that there's one common treatment effect, and each study generates an estimate of this common treatment effect. So on the left-hand side picture is a fixed effect model kind of illustration. So the circle there is the common treatment effect, and you can see for each of the studies, they all have the same treatment effect. And the variation we see among the studies, so for example, study 1, the actual observed treatment effect is sort of far right-hand side with that square. And the difference between the circle and the square, that's the variation we see among the studies, is purely due to sampling error by chance. So in other words, in the fixed effect model, there's no heterogeneity. However, in the random effects model, each study provides an estimate of study-specific treatment effect, and these study-specific treatment effects are not equal. So you see the red dots here, they are not aligned on the same line. They are slightly different, depends on which study it's from. So we are not assuming there's a common treatment effect in this case, but we think these study effects, they are similar, although not the same, but similar. However, we do assume they are exchangeable. And this random effects model models the heterogeneity specifically. So there's two sources of heterogeneity when using random effects model. One is the heterogeneity among the studies, because each study has its own study-specific treatment effects. Another variation is from the sampling error. So the main difference between a fixed effect and a random effects model is how heterogeneity is modeled. In the fixed effect model, it is assumed, as what I said before, the heterogeneity is 0. And in the random effects model, it is not assumed to be 0. A fixed effects model would be appropriate when it is believed that the true treatment effect is in each studies are the same, they are all equal, or it would be appropriate if the objective of the research is to determine whether the treatment had an effect in this observed study, among the studies you included in your analysis. That would be fine. So, however, heterogeneity is generally sort of expected in meta-analysis because we combine studies that have clinical and methodological difference. And the random effects model would be preferred because it allows for heterogeneity in the treatment effects among the studies to be modeled. And it also allows results to be generalized to beyond the studies included in the analysis. So in the UK, the NICE Technology Appraisal Program regularly see companies submission with meta-analysis, pairwise meta-analysis or network meta-analysis. And because most of these appraisals have a very focused decision problem, it's rare to have networks that have lots of treatment or lots of studies. Often this leads to very sparse network, and there's a problem of using random effects model with vague priors in this case of the sparse networks. So I'm going to use a previous NICE technology appraisal to demonstrate the problem. So this is NICE TA163. It was an assessment for clinical and cost effectiveness of infliximab for treating ulcerative colitis in adults. One of the outcomes of interest was colectomy rate at 3 months. So the systematic literature review found there are 2 studies compared infliximab to placebo, and the 2 studies compared cyclosporine to placebo. So using a fixed effect network meta-analysis, the odds ratio of having colectomy at 3 months was estimated 0.72, comparing infliximab to placebo, and uncertainty varies from 0.18 to 2.7. So the result shows that infliximab reduces the odds of having colectomy at 3 months compared to placebo, but this effect is not statistically significant because the interval includes 1. So when using the standard random effects model with a vague prior, the point estimate is quite similar to the fixed effect model analysis, 0.7. However, this is associated now with very large uncertainty in the estimates. It varies from 0.01 to almost 85. So the fixed effect analysis here assumes there's no heterogeneity, but the random effects analysis suggests very high extreme heterogeneity. And this leads to a question of which model we should use. A common scenario we've seen among all the NICE technology appraisals is that the company actually acknowledges most of the time that heterogeneity exists among the included studies. But because there were very few studies to support the estimation of the random effects model or instabilities when doing the random effects model, or the model doesn't converge, hence the company's default to use a fixed effect model. And the EAG's critique often states that too few studies is not a valid justification to use a fixed effect model. So I've done a small review looking at the NICE technology appraisals between 2005 and 2016 to look at what model has been used and what kind of justifications was provided for the model choice. So when performing pairwise meta-analysis, most submissions during that period actually didn't provide any justifications of why they use a fixed effect model. And when performing network meta-analysis, the most frequently used justification for a fixed effect model was insufficient data. So in other words, too few studies or the network is sparse. So the problem with using a fixed effect model or a standard random effects model with vague prior is that the uncertainty associated with the treatment effects may be either underestimated in the fixed effect model case, or overestimated when using a random effects model with vague prior. Although we see in this example, the point estimate is quite similar, but not estimating the uncertainty associated with the treatment effect appropriately could lead to biased results for the incremental cost effectiveness ratio. That could be a quite big problem. So how could we overcome this problem? As there's not enough data to estimate heterogeneity, we can use external information to help us estimating this parameter. This would require the use of a Bayesian approach, because you remember that one of the advantages of a Bayesian approach is that it allows for incorporating external evidence, external information in the form of a prior distribution. And the recent updated NICE methods guide actually also suggests that the use of external information to help estimate this between study heterogeneity in the case of sparse network. So now I'm going to show you how to use elicitation to construct a prior distribution for the between study heterogeneity in the case of sparse network to improve the precision of the treatment effect estimates. So the aim here of the elicitation is to construct a genuine prior beliefs for the parameter representing heterogeneity using external information. So the form of the external information could be empirical evidence. And for example, Turner et al. And Rhodes et al., they have analyzed over 10,000 meta-analyses published from Cochrane database of systematic reviews and propose a prior distribution for the heterogeneity parameter based on their analysis. So we could use that as a prior for our heterogeneity parameter. And the external information could also be in the form of experts' beliefs, experts' opinion. And let me revisit our TA example and show you what I mean, how I think we could use experts' beliefs in this case. So using a random effects model with a vague prior, we see that uncertainty is huge, with the upper bound reaching nearly 85 for the posterior distribution, where the posterior distribution summarizes what we learn from the what we learn about the treatment effect after seeing the data. And then the upper bound is actually over 2,000 for the predictive distribution. And the predictive distribution shows the estimated treatment effect in a new study. So when experts see these results, they may immediately comment on that they do not believe the results, as the treatment effect could not have such a large upper limit. So they don't believe the odds ratio in a study could reach 85, and the odds ratio in a new study going to be conducted in the future could reach more than 2,000. So if experts do not believe the upper limit they see from these results could be plausible, they must have some ideas on what is more reasonable or plausible for the upper limits. And this knowledge would allow us to construct a prior distribution for the heterogeneity parameter. So elicitation in general is not an easy task, but in many fields it has been used and has been used quite successfully to inform important decision makings. And there are many challenges in the whole process. For example, experts recruitment, experts training, managing behaviors during the elicitation workshop. But we do not have time to cover these challenges today. However, I'd like to discuss the technical challenge here, which relates to directly how we could construct our prior distribution. It would be impossible in general to get information from our experts about model parameters directly, because these parameters are very abstract quantities. So for example, in our case, it would be asking experts for their thoughts or opinions on the variance parameter or the standard error of the normal distribution in the random effects model. They would probably just go, what? Yeah, and research have shown that instead of asking opinion about model parameter, it's much better to ask for information on observable quantities, which experts find easier to interpret. So in our case, this would require elicit the range of the treatment effects among studies, and then transform the prior distribution for this range to obtain the prior distribution for the heterogeneity parameter. So let me summarize. Heterogeneity parameter is the ultimate quantity of interest, which is the one we need for our random effects model, and we don't have enough data to estimate it. Hence, we want to construct a prior for this parameter. However, this is an abstract model parameter that experts may find very difficult to express their opinion on. Instead, we ask experts' opinion on the range of the treatment effects, which is observable and easier to interpret. So now I'm going to show you how can we ask opinions for this range of treatment effects and how to transform this information we get on the range to the heterogeneity parameter. I'm afraid I have to introduce some Greek notations, but don't get freaked out. I only have one equation in my slides. So let delta I be the treatment effects in study I, and we have S studies. And this treatment effect could be log odds ratio if the data is binary, or log hazard ratio if we have time to event data, or mean difference if the data is continuous. And in a random effects model, this study's specific treatment effect, the dots here, is assumed to follow a normal distribution with a mean D, which represents the overall treatment effect, the population treatment effect, and a variance tau square, which represents the variation among the studies. So tau here is our heterogeneity parameter. And let's assume our data is binary. So the treatment effect that we are interested in this case is log odds ratio. The ultimate quantity of interest that we would like to elicit is this heterogeneity parameter from the normal distribution tau. As I explained before, normally we do not have an informative prior for the treatment effect D, as we'd like the data to speak to itself. So the only prior distribution we want to construct for is for this heterogeneity parameter tau. In this case, the interpretable observable quantity, which would be the study-specific treatment effect odds ratio, because this is the quantity that our experts will be more familiar with. So I propose to elicit the ratio between the limits of the 95% confidence intervals, and we call this ratio R. So our estimate of the treatment effect odds ratio, it is an uncertain quantity, hence it has a distribution, and the quantity I propose to elicit is the ratio between the upper 95% confidence interval and the lower 95% confidence interval. So this, yes, here is the formula I was talking about, and this is the formula of converting the ratio on the odds ratio scale to the heterogeneity parameter R. So convert R to heterogeneity parameter tau. So this is formula for converting R to tau. I'm not going to go into details of how we derive this, but the message here is that we can use this equation to transfer the opinion on the ratio or the range of the treatment effect to the heterogeneity parameter tau. It would be difficult for experts to express their opinions in the tail area of the distribution, so the either side of the tails, and hence we propose to use a less formal definition for the ratio. So we will just ask the expert the ratio of the largest to the smallest odds ratio that could arise over a set of studies, rather than 95% upper limit and lower limit. And this ratio represents the range of the treatment effect. So let me give you an example. So in our TA, if our experts believes that the ratio R is equal to 10, that means that they believe the largest odds ratio of having colectomy when comparing infliximab to placebo would be 10 times more than the smallest odds ratio in a set of studies. That is, in a set of studies that comparing the two treatments, if the smallest odds ratio observed in a study is 1, then the largest odds ratio in another study is 10. It won't be more than 10. Yeah, because that's the ratio we set at 10. So given this ratio is 10, we can plug 10 in this equation 1 and get what experts believe on the heterogeneity parameter could be. So 10 would be equivalent to, say, tau is equal to 0.6. So that is the transformation between the range of treatment effect and the heterogeneity. Of course, the estimates for the range or ratio R would be uncertain. Experts may believe is more likely to be certain values than other values. For example, experts may believe there's a 50% probability the ratio could be 10, but only 1% probability the ratio could be more than 20. Ultimately, we would like to elicit all these uncertainties and construct a prior distribution to represent experts' opinion of this range R and its uncertainty. However, experts may only be able to tell us their best point estimate of R, or after all the efforts we put in, experts may not be able to tell us their opinion or thoughts in numbers. Although this is the situation we'd like to avoid, as if experts do not believe the results they see using random effects model with a vague prior, like the upper bound being nearly 85 or over 2000 in the predictive distribution, then they must believe something else which is more reasonable and plausible, and that's the number we're trying to get. So I have developed a 3-stage procedure for elicitation to overcome the cases where experts are not able to provide the full distribution for this range with uncertainties. So this is the 3-stage procedure. The first stage is to confirm there is a need for doing a random effects model. And if that's the case, we move to the second stage to elicit opinion for the upper bound for this ratio. So we're not asking for their best estimate, but asking what maximum value could be for this ratio. So if experts cannot provide such information, but believe that a random effects model is appropriate, then we use Turner's prior. So Turner, as I said before, they've analyzed loads of meta-analyses and come up with a prior distribution for tau, and we use that in this case. And if experts can provide this upper bound, for example, if the maximum value for this ratio is 10, that means that odds ratio in one study cannot be more than 10 times of another We then could move on to the third step, asking experts if they could provide a full distribution for this ratio. And if the upper bound for the ratio is the only information that experts could provide, then we could use this information together with Turner's prior to derive a truncated Turner prior, which eliminates some of the extreme values within the Turner prior itself. And I have an example later to show you how this works. And if experts are able to provide the full distribution for the ratio, then we go ahead with eliciting the prior distribution for this ratio R. So the the three-stage procedure is: first stage, determine whether we actually need a random effects model. If not, we go for the fixed effect model. If yes, then we move to the second step to elicit an upper bound, the maximum value for this ratio. And if experts cannot provide the information, then we use a Turner prior. If experts can provide that information, then we ask whether they could provide a full distribution. If they can't provide a full distribution, we use the maximum value for the ratio elicited from the second stage, combining with Turner's prior, and get a truncated Turner. And if they can provide a full distribution, we go ahead with eliciting a prior distribution for tau. I do not have time to go through eliciting a probability distribution in detail today. There is an R package called SHELF, the Sheffield Elicitation Framework, developed by Tony O'Hagan and Jeremy Oakley, which is for elicitation in general, and there is a function for eliciting between study heterogeneity using a roulette method. So this is a screenshot of what you would see when you open that app, the Shiny app. So in this case, we are asking experts to provide their judgments about ratio of the largest to the smallest treatment effect, and then the program behind the thing will turn this histogram into a parametric distribution, which is the prior distribution for this ratio or the range of the treatment effect, and then will transform this prior distribution to a prior distribution for tau, which is for the heterogeneity parameter. It also provides feedbacks about the probability of heterogeneity being low, moderate, high, and extreme, given the elicited prior distribution for the heterogeneity parameter. And more details can be found from my paper there. So now I'm going to show you the reanalysis results of this NICE TA 163 using a random effects model with a vague prior and also some informative priors. We're using 3 informative priors here. One is the Turner prior, the second one is the truncated Turner prior using the upper bound we've elicited from the expert. And the final prior is a fully elicited prior distribution for the heterogeneity parameter. So this is the results. So you can see, as in the other case before, all the point estimates are quite similar, regardless of what model is being used or what prior is being used. But the uncertainty associated with these estimates varies a lot, depends on what's been modeled and what prior is being used. This table also shows the probability of heterogeneity being low, moderate, high, and extreme. And when we are using a vague prior, there's a huge probability, like 87% probability that the heterogeneity being extreme. So what do we mean by heterogeneity being extreme here? That means the ratio between the largest and the smallest odds ratio is more than 300. So in a set of studies, if the smallest odds ratio is 1, then you would find the largest odds ratio in this set of studies would be more than 300, and that is not plausible in this particular case. And when using Turner's prior, there's still some probability, like 8% of the heterogeneity being extreme. And these large probabilities of heterogeneity being extreme would lead to implausible estimates of uncertainties for the treatment effect we see here. So especially with vague priors, the upper bound is nearly 85. But when we use truncated Turner prior, the truncation makes sure that we get rid of all the extreme heterogeneities, hence the probability of heterogeneity being extreme is 0. And also with this particular elicited full distribution, the probability of heterogeneity being extreme is also 0. So far I've covered this elicitation framework for binary outcomes. It can also be used for other types of outcomes, but when using it for other types of outcomes, there are more transformations is required, so it's a bit more complicated, but you can find details from my paper. So to summarize, the choice between a fixed effect and random effects meta-analysis or network meta-analysis model depends on the inferences required and not on the number of available studies. A genuine prior distribution for between study heterogeneity should be used to avoid making misleading inferences. And the minimum requirements here is the ratio of the largest to the smallest odds ratio if the outcome is binary. So the fixed effect and the random effects with vague prior, they actually provide results in two extreme ends. One assumes no heterogeneity, the other one is associated with very implausible extreme heterogeneity. The true variability of the treatment effects lies somewhere in between these two extreme ends. So the three-stage elicitation framework using external evidence can help you to determine where more plausible values for the variability should lie on this kind of line. And in turn, it improves the quality of the inferences in the decision making. So these are the references I've listed in the slides. So the first one is the paper we published a few years ago, which details how to construct a prior distribution for the between study heterogeneity in the case of sparse network. And the second reference is the use of the Sheffield elicitation framework. And the last two references are the empirical evidence Turner and Rhodes et al. Generated by analyzing lots of meta-analysis. Oh, and thank you. That's the end of my talk.
Okay, thanks so much for that, Kate. Okay, we do have, I think, one question so far, or it's actually kind of a couple of questions wrapped up together. So I'll read that out. Just give me a moment. Louisa says, if there's little data in existence, then who would the experts be? If there's someone close to the technology that's been developed, they might be biased and inclined to exaggerate the upper estimate of the odds ratio.
Yeah, so the experts in this particular context could be clinical experts, members of NICE committees, the analysts from the company side, or the members of the evidence review group. In general, if somebody have some knowledge about the treatments being appraised in this particular kind of disease area, and hence after seeing the evidence, they would have some knowledge about, the range of the treatment effect, how much it could vary. Would we ever see an odds ratio reaching over 100. Perhaps not. Like in most of the cases I've seen in HTA, 10 or 15 or 50 could be used as a sort of the upper bound to truncate the Turner priors.
Okay, thanks for that, Kate. And Louise also asked, and she does stress that she's new to this idea and apologises if the question seems obvious, but how does a higher estimated upper bound for the prior affect the posterior? Would it make it more or less uncertain?
It will make it less uncertain because I so because it gets rid of the extreme end. So I'm using this distribution here. So if you look that if we use a standard Turner prior, the orange parts will be a bit bigger, say, and then when using the truncation, you chop, like if we truncate at 0.5, and you get rid of everything on the right-hand side of the 0.5. Hence, you have a strong prior beliefs it's less than 0.5, and that will be reflected in the uncertainty estimated in the posterior. So it will make the credible intervals narrower. And in a way, that's the whole point of using an informative prior here, is to make the range narrower and more plausible.
Okay, thanks, Kate. We also have a question from Chloe, who asks, to use a fixed effect model, is the main requirement that the results of the fixed and random effects models are congruent?
So to use there are two kind of cases you could use a fixed effect model. Firstly, is there's genuine belief of all the studies estimating the same treatment effect. There's only one treatment effect here. It's quite rare, but it may be possible. Say companies run a few early trials and it's all in the same kind of protocols, etc. Then you may believe the treatment effect they're estimating is equal. Another case to use the fixed effect model is you want to estimate whether the treatment works in the studies you included in your analysis. So in this small pool of observed studies, you want to see whether the treatment effect, the treatment works, and you can use fixed effect model.
Okay, thanks, Kate. We have a question from Evangelos. Evangelos, I know your name from the HTA program. He asks, it seems the fixed effects model was good to rely upon and much easier to use. Has there been an extensive comparison for the two approaches in practice?
That is a good question, yes, because it's easy to use, and it is an easy option to default to. That's why in submissions we often see when there's not many studies, companies just default to use the fixed effects model. But it's not going to provide you an estimate with the uncertainty estimated appropriately, because it assumes there's no heterogeneity. So the credible interval or confidence interval would be much narrower than it should have been.
Okay, I think that concludes all of the questions that we've had so far. So thanks everyone for, oh no, there's another one from Annie. The minute I wrap it up, the questions come. Okay. Kate, can you see the questions in the chat?
Oh, is it say that the credible interval obtained from Turner and the elicitation are very different? Is that a way to validate or decide which one is more plausible? Validate, unless you run loads of analysis in this particular kind of research problems or decision problems, and then you would see what the actual estimate is. Otherwise, there's no way to validate it. I think here is a question of what you would believe would be more appropriate, because Turner's prior is a very general one. They look at the meta-analysis regardless of the disease areas or treatment. maybe if your experts has more knowledge for this more focused problem, they may well be a better one to use. But when it comes to use informative priors, it is a good practice to do sensitivity analysis, hence to show how sensitive your actual results is to, you know, the change of the prior distribution.
Okay, thanks, Kate. Okay, I think if that is all the questions, oh no, there isn't. Okay, Owen says, when acting as an EIG for a NICE appraisal, would you look to rerun the whole meta-analysis if one was submitted by the company and all the necessary evidence was provided, or just review their methods as a whole?
Often I would ask for, if it's not been submitted, I would ask for their data, their code, so that as an EAG we can assess whether they've used the right data, they use the right model, the right methods, and if they've run a fixed effect model due to the sparse network, I would ask them to rerun using a random effects model with appropriate prior distributions. Yeah, I think that answers the question.
Okay,
yeah.
Thanks for that. Okay, I think at that point we'll bring it to a conclusion then. Thanks everyone for coming along today, and obviously I hope you'll join us in November with Dr. Stephen Harris or in December with Dr. John Richmond. But thanks for joining us today, and for everybody's participation as well. It's always great when we get some really good challenging questions. Thanks very much.